Yo, what's up, welcome back. Today we're working on my x86 operating system written in Rust, titled StreamOS, because it's an operating system we're developing on Stream, I guess. It's written for fun, whatever fun means in this context. And what we have right now is we have this like operating system that I can boot in a virtual machine. I'm using QEMU. I assume that there's probably stuff that would break if I tried to use a different virtual machine, whatever. We have like this like little brick breaker demo, as well as this like HTTP server that's running. If I look at the IP of the thing, I see like hello from the kernel. We're servicing basic HTTP requests, and I say like hello, and I get back that like, oh, we do see like the OS is sending us back something with that data, like with the data we're receiving. So we've got some sort of HTTP, which requires like TCP and ARP for like address resolution, Ethernet, and the Ethernet card requires PCI. We have like multi-core support, we have clock support, we have memory allocation, as well as like some form of concurrency, right? Like this server is running at the same time as like this brick breaker demo. We have unit testing and logging, so where logging does like logs to the serial console, and the virtual machine forwards that to standard input output. Yeah, so kind of chilling there. What we're working on today is USB support. So over the past couple streams, we've been kind of like working on getting any form of communication happening with the device, and we've parsed this like device descriptor from a mouse that we've plugged in. We've got like our virtual machine has like a virtual mouse that's being acting as a USB tablet, and we have this like device descriptor that we've read from it that is at least like confirming that we have like some form of USB working correctly. We've been referencing this book, USB, the Universal Serial Bus book that this guy wrote. And he's got like a GitHub project that we've kind of been referencing. I suggest reading the book as well if you like are trying to do this type of thing yourself. The book was very informative and helped me like piece everything together for sure, compared to like OS Dev Wiki, which was a lot harder to piece together with. And where are we at? So the way it looks right now, current mental model. I've got my computer, CPU. He finds a USB card, B card. This guy is like plugged into the mouse. And this card is like connected via PCI to the CPU, as well as through memory. So the idea is we like enumerate our PCI bus. We find an ID of like a USB card. This is like a UHCI USB card, which means like the interface for USB 1.1 cards, I think. We talk to it over PCI and say like, hey, what are you? And he was like, hey, I'm a USB card, and like, here's my registers. We like set up like a pool of memory, and we like inform him. We say, hey, this chunk of memory over here, this is yours now. And what happens is he like iterates over that chunk of memory, and he says like, this is a list of things to do, and I'm going to do the thing that you say to do in here once per millisecond. I'm just going to go like 1 millisecond here, 1 millisecond here, 1 millisecond here. Each of these guys right now, we have them pointed to like a queue, like the same queue of work. So we have like another queue of work that says like work to do, and each element in here points to that same queue of work. So all we do right now is we like append work to this queue, like this. No. Every time we want to like send a packet, receive a packet, whatever, we say like, hey, could you read this device? And this will automatically like propagate. Like, so he'll like once per millisecond pull this thing and be like, okay, time to do work now. And so that's kind of where we're sitting. We have a little bit of buffer ownership problems with this still. So the idea is like you have like this like buffer, and you pass it off to the USB card, and at some point you like check later and you go like, did you write to it? And he goes like, yeah, I wrote to it, we're good to go. Or like, I read from it, I passed that on. But it's like not very obvious how you're supposed to like communicate that to Rust. Like the compiler, he might say, oh, you wrote to this buffer, but then you never read from it. So like, I'll just not write it because fuck it, who cares, right? And so you're supposed to use these like volatile writes to like prove to the Rust, say like, look, I know that you think that like this is like something that you don't need to worry about, but like do this right for real. And so one thing I want to do is make sure that like our like writing is correct. We have like a driver stack kind of that like, how do I say this? If I have like a user user's the wrong word. If I am a consumer of this USB driver, right? So I have like USB and say I'm like mouse driver. If I want to like say read this buffer or like run this thing, here's like a chunk of memory, fill it with whatever the device says. The USB driver like passes that off to the hardware. And right now what we're doing is we're like kind of like taking a reference to this buffer and storing him like here as well as in here, and then that buffer also gets kind of propagated to the hardware. And that makes it kind of hard for this guy to like modify stuff. Rust kind of assumes single ownership of anything, and this kind of like breaks that guarantee. So one of the things that I want to do today is kind of make sure that this gets like properly passed from here to here, properly passed from here to here, and then properly makes it like back over to here. And I think I'll understand a way to do that. So one thing I want to do is fix that. We have one of the things that we have to do when we talk to USB devices, we have to like initialize it and like give it an address, right? Like all of these USB things are like on the same bus. And we need to like, if we say like, I want to talk to the mouse, you say mouse address, please respond to this. But the mouse doesn't have an address when it's booted up. So we have to like assign it that. And we haven't really like started implementing this like mouse driver at all. And so that's kind of the other thing that we want to get into. Is like at least like prove that we can get a position or something. So I think that's kind of where I want to start. I'm going to start with like this packet management stuff because I think I have something that's like pretty quick to implement there. Then we'll start looking at like device initialization, and then if we finish that up and there's still time, then we'll probably start trying to get like prove that we are getting a like actual mouse position from the mouse. So let's start working on what are we going to call it? Buffer ownership fixes. Okay. So last stream, what we started doing was we have this like UHCI card and UHCI card driver, and we're kind of working right now all like in this kind of stubbed out sample code. Or I shouldn't say stubbed out, like this like we haven't really flushed out who's going to be a consumer of this driver right now, but we're just kind of like running through this stuff. So on initialization, we say, could you get the descriptor for the device that's plugged into this port? And in there, we generate these things called like transfer descriptors. So back in this guy, these guys would be called transfer descriptors. This would be called a queue, and this would be called like a frame pointer or frame list or something. And so what we do is we like generate some work to do, these like transfer descriptors, where we call USB setup, which this like a type of packet, but we're basically saying like, hey, could you tell me about yourself? Tell me about yourself is what this buffer says. Give me a device descriptor. And then here we say, could you like read that thing back? We like staple that work together and we put it onto our queue of work to do. Then what happens is like this thing that we pass in is a vector of heap allocated storage, but what we get back is like shared references to that storage, and then we're kind of saying like, hey, just assume that after some amount of time that will change and copy that into somewhere else. And what I would like to do is like not do this copy. I would like to maybe pass the buffers in and maybe get them back out as like a future is kind of what I'm thinking, right? So then we can say, instead of having this sleep here where we're just like, we sleep for 2 seconds and just hope to fucking God it's done. What we want to do instead is we want to like have maybe say await, and we just like get the things back, but we know that they're in like the finished state now. That's kind of what I was thinking. And so what does that look like? Let's think. So something that we need to be careful about is in our driver itself, we need to like hold onto the buffer. So if we have like mouse driver, USB driver, when he requests that he writes to hardware, this guy has to like hold onto the buffer in memory, because if this guy drops the buffer, what's going to happen is we're going to have like USB hardware, and he's going to like try to write to it. But if it's just like some buffer out like here, and the mouse guy is the only one talking, like holding onto it, he's going to try to write to it. But if the mouse driver is just like, fuck it, I don't care anymore, and drops it, then like he still needs like valid memory to write. So the USB driver has to like take ownership of it. And then once it's done, we have to pass it back. And so when we append this work, we're going to take in the work to do. And these like this data type that we have, this transfer descriptor storage, this is just like the descriptor that we pass to the card, as well as like the buffer that it's pointing to. So we need to store that in the driver, and then take it back out when it's done, probably. So we need to think about what that looks like. So I guess let's start with like, what does the output of this function look like? It looks like a queued work future, I guess, or like USB future, we'll just call it for now. And what it's gonna do is it's gonna implement future, which is like Rust's way of saying like, this will happen later. Like this is good. Like I will give you something, and at some point it will change state. Which means that we need to use Rust's future trait, which means that we need a future, as well as some of the like queuing stuff around it. So we have task poll, and I think task context is the other thing we need. Here we implement this interface, and we'll say the output of this thing is a vector of box transfer descriptor storage. Right, so when you're done, when we finish looking at hardware, you'll just get the thing you pass us back, right? Because when we say append work, that's like the same type that we pass in. How will we know if it's done? And we'll know if it's done if every element in here has their status bit set by the hardware as finished. So we can go let finished is equal to self.buffers. Okay. So what are we're gonna have buffers here, and what are they gonna be? I guess because we were saying that we need to keep track of them, we need to like store them in here in our like work. Maybe these will be like arc ref cells or something. We can't use ref cells because ref cells are not thread safe, but we need something. I was gonna say we need like something that guarantees that this is exclusive ownership, but maybe we don't. We're only reading here. Hardware's the only person writing to them. But I guess we need to say to Rust, hey, make fucking sure that how do I say this? Rust assumes that if you have an immutable reference, that mutable references can't be used. But the hardware is going to be changing stuff under the hood. So you use unsafe cells to like flag to Rust that the thing inside might be changed. Which I think makes sense. Or you could use like volatile read and writes as pointers. So maybe we do that. We say we have a shared reference to a box to a vector boxed transfer descriptor storage. So here we'll know it's ready if we iterate over all of these buffers and do volatile read on their status bits. Okay. So how do we do that? Sorry, I'm thinking here. So we have on these guys for item in self buffers. This is not an iterator, he says. Can I iterate on him? Yes, I can. We have like item status, descriptor status. And this will like read the bits in the descriptor and check their status. And we can say get bit. I know that there's the status bit for the USB is, I think, the last bit. Let's see. UHCI OSDev. Give it a sec. This is going to take a while. Maybe I look up UHCI spec PDF because the OSDev wiki seems to be slow today. Here we have our transfer descriptor, and one of the things that they have in here is status, which is bits 23 to 16, and 23 is the thing that we are keeping track of. So bit 23 here says set to 1 by software to enable execution of a message transaction by the host controller. When the transaction with this descriptor is completed, the host controller sets this bit to 0. So basically we're waiting for this guy to be 0. So we can say get bit 23. Now the problem here is that this isn't a volatile read of the status register. And so the question is like, how do we make sure that this is volatile? And I guess we could put this as unsafe cell. Because that would force Rust to actually read the value. But that's still maybe not good enough. We might actually need it to be a volatile read. I'm not actually sure, because unsafe cell does tell him, like, hey, someone might be mutating this under the hood. But I don't know if that's a good enough guarantee. We actually might need to just like cast this. We might need this guy to do a volatile read inside, but I don't really want that because like I might want to be like looking at the descriptor and polling things on him even without that. So maybe what we do is we copy it out. So we say item descriptor 0. And we just look at this bit manually. We can say this is as const u32. So we'll say let status word is equal to this. And we'll do a volatile read on him. Is this right? Do I need to put an ampersand here? I think I do, but for some reason this is working either way, which is kind of confusing to me. And then we'll say, yeah, this is unfortunate. We're kind of like bypassing this, but that's okay. We'll say status word get bit 23. Okay, and we'll say if this is set, then we are not ready. Right, like there's still work to do. Otherwise, if we get through all of them, we return pull ready. And we have to be ready to extract this guy back. So maybe this guy, instead of being an arc, maybe we can somehow tie him to his actual storage. Like maybe we can do this. Which is the storage somewhere. Our master queue has buffs that is vec. We'll put them to box for now. And maybe we'll say that our buffer range is a range that we're going to iterate through. So we'll say core ops range, which I think needs to say that we're a range of use sizes. I was going to say then we can like pop those out of this vector, but this is actually getting a little trickier because if you have like if you pop stuff out of the vector that the UHCI guy is holding, so he's got like Q storage that has a vector of these guys, right? If you were to like pop stuff out of him, all of these like the IDs of all of these guys would change. So maybe we'll do like a hash map of usize to this. That way everybody will have like a constant ID. Is that what I want? Thinking. Let me think about that. That seems maybe more reasonable. Because then what we can do is we store the IDs here in our future, and we check the buffers that we care about, and if those buffers are ready, then we pop them out and return them. All of this just because if we can't store the buffers in this future itself, because if we drop the future without it finishing, then the USB hardware will not work correctly. So this is why we have to do this. Okay, so I think this might work. So here, we'll just say unimplemented for a second. And I just want to start patching up compile errors because there's going to be a lot of them right now. And I just want to get into like a somewhat useful state. So part of this is that we are assuming that we have like a contiguous queue of work at some point. When we're appending work, basically what we do is we take the last element and we point it to the new stuff. So we have to maybe, if we make this a B tree map, then we have sorted order, which might work a little better. So we'll use alloc collections B tree map. And I think that some of this stuff will work now. At 248, we have a problem. So that's here. We'll just comment out this stuff for now because we are in flux on that. 313, we are creating a vector, but now we know that this is a B tree map. At 335, we're sticking work in this queue. And we need to fix that. So this guy doesn't have like a last mute on his B tree map. So what does he have? Does he have a way for us to like get the last element? B tree map. Does he have like a last entry? That's probably what we want. Or last key value. Last entry is what we want because we want to change. We want to be able to. I guess it doesn't. Yeah, we want to be able to mutate it, I think. And so what does this guy return? He returns a option occupied entry. So here we say probably like key. No, he doesn't like that. So what is this thing? This is a occupied entry of key to value. So what are the APIs on this guy? He's got key, remove entry, get mute, into mute. That's probably what we want. Let td equals td.into mute. And I think the rest of this stuff will work down here. Yep. And then we insert this stuff. So we need to keep track of like the last ID. Which will make a U64. We can't use usize actually because that's going to be a 32-bit value, which will run out of room. But if we use U64, we're chilling. Then we say our initial ID is 0. But here we're going to say, take all of the work, map it to value, takes in self, last ID, and the value. But we're also going to have to increment last ID. So we'll say let ret is equal to this. Okay. And we'll say this is an iterator of stuff. And we'll extend this with the iterator. This guy is going to return nothing for now. And we'll say, well, I guess this is going to return USB future. Associated with the lifetime of myself, but we can just kind of sub it out. And then we can say unimplemented here. And let's check for compiler. So he doesn't like this because I didn't use work into iter here. I wasn't consuming the data. And we're close now. So now all we have to do is write await here, I think. Remove this sleep. And I think everything compiles now. And so now we can go back to just fixing the unimplemented stuff. Solid, solid, solid. So here, our USB future, where is this guy? So we need to construct him. So what do we do here? We'll say let future is a USB future. And I guess we don't really understand what his insides are going to look like yet, so we'll just kind of chill. We actually won't implement that yet. And instead we're going to like look at, well, what do we want this guy to look like inside? So we have our IDs, we have the mutable reference to the buffers, and we can say we'll say for ID in self.IDs, we're going to say let item is buffers get self buffers get ID. And we'll assert that these are valid. If they're not valid, then something's gone like terribly, terribly wrong. So we'll say invalid ID for USB storage. And what doesn't it like here? Cargo check. Let's just double see. So he doesn't like that. Maybe I have to write ID like this. Nice. Yeah, I do. Solid. I accidentally had like a double borrow in there. Now we still have this stuff where we check the status bit. I'll say if bit 23 is set, the USB hardware hasn't flagged this descriptor as serviced yet. Cool. Now what? Now what? We then say, if we got to the end of this, then we can just pull all these guys out. So we'll say for ID in self.IDs, self.buffers remove ID. And we'll say we have like a return. We say we push that thing into the return. And then we return ret. So we say pull ready return. we have to, if we cannot remove that thing, something's gone terribly wrong. So we'll say failed to remove ID. And it doesn't like that we are using self as mutable and immutable, which is interesting. I didn't think that would be a problem. Can we just say clone? Then we need to remove this guy with an ampersand. Do we need to write mute self here? Is that allowed? Yeah, it does seem like that's allowed. And if I go back to not cloning this, does that work? Cargo check. Remove this ampersand. Yeah, it doesn't like that. That's annoying. Well, I don't really want to clone this. Can I do like, how do I iterate over this and mutate this guy? Can I say like let IDs is equal to self.IDs and let buffers is equal to and mute self.buffers? Is that allowed? Or I guess I don't even do this. I can just do that, and then I say for ID in IDs and buffers remove. Consider borrowing here. Why? Why? Move occurs because this type has this. Oh. If I write and mute here, yeah, okay, it doesn't like that. So it's kind of annoying that it doesn't let me iterate over the IDs as well as the buffers. But we'll just clone the IDs for now. There's a better way around this, but I'm not going to deal with it. That's fine. Doesn't matter. Okay, so now we've like iterated over all of the we've pulled out all of the transfer descriptor storages and we've returned them. And so now all we have to do is create this USB future. So we'll say USB future buffers is self master queue buffs borrowed as mutable, and IDs is a vector of IDs that we've just allocated here. So we'll say let IDs is, I guess we need to iterate over work, the work that we've passed in. So we'll, I guess, enumerate the work. I don't know. Work.len is probably what we want to do. Is we want to say 0 to work.len, and then we map the value to the value plus self.lastID. Then we say we need to convert this to a U64. And then we say ID self last ID plus equals work.len. Great. As U64. Okay. Then here, instead of doing this last ID shit, we zip these guys together probably. So we say like what? IDs into iter zip work into iter or something. I guess we have to clone this guy. Okay, then we can extend this, and then our IDs is IDs. Okay, so we're close here. This guy needs a collect on him to turn him into a vector. And this guy doesn't like that he's a USB future. He's expecting a hash map. But this should be a B tree map. What's wrong now? Cargo check. So he expected mute B tree map box. Instead, he found, oh, because he still had a U size somewhere. Instead of U64, There we go. And our IDs, he thinks he's a U size, but he expected U64, so the same shit. This needs to be U64. So shockingly, everything works here. Now the only piece of info that we're missing, yo, what's up? Is when we pull this guy and he says that he's not ready, that means that like our executor will go, oh, he's not ready. Somebody will tell us when he is. And nobody will. And so what we have to do is we have to like make sure that we enable interrupts here and we correctly wake up whoever's waiting. Is there a way to kind of get out of that for now? We might be able to just stick it on a timer for a little bit. I might try to do that. Or is there something else I could do? We could enable interrupts. So there's this like thing on the USB controller. In UHCI, you can put something into your transaction descriptor that says interrupt on complete. And this says that the interrupt controller should issue an interrupt on completion of the frame in which this transfer descriptor is executed, even if the active bit in the TD is already cleared. And I'm wondering if there's a way for me to like make that happen here. I think probably what I'll do instead is I'll try to do like just stick it on a timer, sleep for a little bit, and check every 4 milliseconds or something. Just because that's easier to pipe through before we enable interrupts on the controller. We haven't like worked with the controller's interrupts yet, and so I don't really want to deal with that if I don't have to. Instead, I can probably just use our like sleep mechanism. So I think there's like a wake up requester. And here we can just say register wake up time. Yeah. Which means that we also need a our reference to the current clock. And so here we can probably just say what? Self time is equal, self time get is the current tick. And we'll say let wake up tick is the tick plus, I don't know, we'll say like 100 milliseconds times the tick frequency. This needs to be as F32, I think. Cool. And then we say wake up requester register wake up time as wake up tick as usize. Cast them back. I think that works. So I think that that'll end up with us waking up. Oh, but this guy is an async function, so we just pull. Is that right? Why is this compiling? Oh, it's not. USB future is missing some stuff, so we pass it in. So we say here, we pass in a reference to the time. Is this in protected mode or long mode? Protected. 32-bit. Self time clone. Maybe someday we'll add 64-bit, but we're... this seemed simpler at this point in time. And we pass in the wake up requester, which is self wake up requester clone. Okay, so now he's mad because this guy's not being used correctly. So we just, I think we can say let feud is this, and we say, oh god, is this right? This seems kind of right. So we can just say poll future. So let feud is equal to core pin feud, and then we say feud poll with cx, and then ignore the result. I think that this will result in us getting woken up at the correct time. We'll have to check. Maybe what we'll do here is we'll just print here if we're getting polled. So we'll say print line USB future polled. And I think now if I run this, we should start seeing USB feature polled logs. I think. Let's see. Oh yeah, hey, nice. That's kind of nice. We see USB future polled twice, and we get the descriptor back. Wow, that actually went a lot cleaner than I thought. So I think that we've kind of just pushed everything together so that our buffer management is working correctly. And now the only thing that I want to do is I want to say that like when we're finished, I actually want to make sure that we're doing volatile reads of all that memory. Because like there's a chance that the Rust compiler goes like, I don't know, man. And so I think what we can do is we can say let buff is equal to self buffer is remove. We remove the thing, so we just copy paste what's in here. And now, like, everything in this buffer, there's a chance that it's, how do I say this? We need to make sure that it's, like, synced with what hardware wrote. So we can say, impl transfer descriptor storage. And I think you can just say, we could make something that's, like, sync, hardware sync. And we're getting crazy in here. We're going to say, for item in mute self.descriptor.0. So we have like a buffer of U32s. We're going to say item equals item as mute U32 read volatile. And I think that this will force Rust to not optimize out this read. And then after everything after this, it can optimize whatever it wants. We don't really give a shit. But I think this will force it to do an actual fetch of memory going forward from this point. But I could be wrong. This seems like a trick to do. I'm kind of guessing, though. And we'll do the same thing for the buffer. And this is mute U8 no. So now I think that we can just do buff hardware sync and push the buffer back. Now, hopefully this guarantees to us that the buffer that we read back from hardware is like being processed correctly by Rust. That's my hope. But otherwise, it seems like we've kind of just solved the buffer management for now. Oh, the only thing here is this guy is using, we had this like fix me broken as all hell thing, and I think this can just go away now. I think that this is safe. Yeah, no more pointer manipulation bullshit. No more violating mutability guarantees. Okay. So what's the next thing that we want to work on now? We've kind of fixed the buffer ownership, so maybe, actually, before we move on from this, we'll just do a little git add u git commit -m checkpoint time. And the next thing to do is, I guess, start trying to, like, assign USB IDs and stuff. So we'll say, 4445, properly initialize. We want to properly initialize the USB device, which involves like setting its address and shit. So here we have like somewhere we have get descriptor. Oh, we don't need this volatile read anymore as well. We can just output work one dot, fuck, what was this thing? This guy is a transfer descriptor storage, so we can output work one buff or something. Let me just cargo run this, make sure everything's still in good order. Hopefully we still see a valid USB descriptor come back from the device. Length 12, BCD version 2. Yeah, this is good. That looks good. And I think that if I stick it into less, we can actually like read the stuff that we want to see on it. Right, we see like vendor ID 627, product ID 1. This matches what QEMU says that our USB tablet should be. Cool, 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 cool. All right. So I think now we're in kind of like a spot where we can start just throwing packets at it. And hopefully that will start, like it'll be easy to iterate now with this workflow. That's what I'm hoping. So let's look at this guy's GitHub again. And in here, I think it was under USB, utils, device discovery, UHCI. I wanted to look at, we're missing a couple things here. One thing we're missing is we are not acking our read response, like device descriptor read correctly, which I think is a part of the protocol that we have to follow. So I'm just going to quickly throw that in here as well. So here we're going to say let act td is equal to generate td 0 0 PID out. This is an output thing. Our buffer is going to be a vector of size 0. And I think that's actually it. I think everything else in here we don't have to set. So this is just the same as the previous thing. This is the same as the previous thing. He has 1 shifted left by 24 here, which is a new thing. What is that? So if we look at the transfer descriptor, that was in the second word. He has 1 shifted left by 24. He's setting the interrupt incomplete. Okay, we don't care about that. We're not using interrupts right now, so that's fine. And here he's using an output PID. The address is still the same. He's just setting, what is 1 shift left by 19? This is the packet size 0, so that's automatically handled by us. And so I just want to look at this 1 shift left by 19 to make sure it's not something crazy. Which would be here on the third word. Data toggle. Oh, that's interesting. So we actually have to set the data toggle on here. So we'll just say, we'll figure this out later. Eventually, we're going to have to automatically toggle data. So we'll say, fix me automatically handle data toggle. Actually, I think we can do this. Yeah, we'll just do it now. Act, and so we'll say act td descriptor. Oh, sorry, this has to be expected and say invalid act packet. And here we say act td descriptor set data toggle true. I don't know if we should do this automatically or not, but the fact that it's broken right now is a problem. So what happens is in the USB spec, every packet you send, you're supposed to flip this data toggle bit so that it knows that it's like reading things in the right order, I think. I'm not really positive why that exists, but all I know is you have to alternate between packets. And we weren't doing that. Okay. So if I cargo run now, do we still see a response happen? Yep, we still get our descriptor. It still looks sane. And now the thing to do is try to actually initialize it. So here he calls this like UHCI set address function, I'm pretty sure. He gets the descriptor, then sets the address. He does reset the port again, which is kind of weird. I wonder why he does that. Probably a like, that's maybe a compatibility thing. I imagine that you don't have to do that every time. So I'm just going to do a UHCI set address directly and see if that works. So what does he do in this? He sets up 2 transfer descriptors, one of which is a setup token with this packet info in it. Okay, so our setup packet, third byte replaced below. And we could probably just take a look. We can probably take a guess at what this is. So the second thing he's doing is a 0-sized read. and he's just putting those back to back. So we could probably guess that he is trying to do a set address call. So probably we could look at like the USB stuff on OSDevWiki and look for that setup packet. This is kind of annoying because the OSDevWiki has been really slow recently. So while that page loads, I think I'm just going to go to the washroom really quick, since I might as well use this time for something productive, like peeing. Be right back. And we're back. All right. So we're trying to figure out how to set the address to this guy. So we can assume that this guy is sending this packet. So we'll see that in a sec. He's sending 0005, so that matches this, 00 number 5. Then he sets the address, the index, and the length. So what the fuck are index and length here? W value specifies the address to be assigned to the device. Cool. The behavior of the device is undefined when W value specifies an address greater than 127. Okay. But what are these like index and length fields? Index. Yeah, it doesn't really. Oh, it's like maybe it's a thing that's on all. I see. So this is a thing that's on all setup requests, and we can probably just set it to whatever, which is probably what this guy did here. Is he just set it to 0? So here he's got device address is going to be these guys. The index is going to be this, and the length is going to be this. Got it. Got it. And so he's probably setting the address based off of some allocator. So for now, we're going to assume that we're the only people setting the address. So we can just pick anything. But eventually we're going to have to do some sort of like address allocation mechanism. But we can skip that for now. So we can say let address setup packet is equal to 0x00, 0x05. Then we need a address. So this is a little endian. So we're just going to set it to 1 for now. And what was the next thing? Index, we're just set to 0. And then we have to set the length. And it looks like he's set the length to 0, which kind of makes sense if the response, I see. So this is like the length of the response, maybe. If I remember correctly, in this setup packet, the one from before, we specified the length of the response. So maybe because we're saying that we are not expecting to read anything back, the length of the response is 0. Then we just say setup TD and act TD. And this is going to be the address setup packet. This is going to be a setup. It's going to be issued to address 00. And now the question is, does he issue the ACK also to address 00, or does the ACK go to the new address that was just set? Looks like 0, I think. dev address. Yeah, it does look like he sends them both to 0. Okay, so maybe let's do that work and await it. Like this. And then I guess then we can get the descriptor again at the new address and see if that works. So we'll just do all of this descriptor shit again. Right, like this. And see if, so I guess reading it at 0, the address 0, should fail now because we've set the address to something else. So I think that if we do this, we should probably see some like garbage come back. So let's see. Okay, so it's booted, it's run some shit. We do see the same descriptor again, which is a little concerning. I wonder why, because here we should have seen the address change. Let's see what happens if I try to read from address 1 this time. Let's see. So on the second one, oh, that's interesting. It's actually never completing. Presumably because the USB card isn't setting those buffers of service because it's like trying to talk to card number 1 and card number 1's not responding or something. That's my guess. Sorry, address 1. Most probably because this setup address request didn't succeed for some reason. So I wonder why that is. So let's make sure that we handle this correctly. Nothing in here is looking too fishy to me. What is this? 121 and 0 should. Oh, do we have to set data toggle? That's possible. This is bit 19. So he does set data toggle on the second thing. So maybe here we have to set data toggle on our ACK. And it doesn't like that because this isn't mutable. Let's try that one. Still no dice. Okay. Interesting. Interesting. I wonder if we reset the port again, like they do in their example, if that changes anything. I wonder if maybe that's like a required part. Maybe the set address has to be like the first thing that it sees. Doesn't look like it. Doesn't look like it. Let's just see if we ever get here. Hello, Mick, is what we'll say, just to prove to ourselves that we're getting past that like address set request, which I actually don't see, which is interesting. Do we get to right before it? That's interesting. I'm just not seeing that at all. Okay, so where are we getting to? What the fuck? Okay, so we get to the first hello Mick. We print the descriptor. And so this reset port is never finishing. Oh, is this like a bug? Are we hitting that sleep bug again? Where like sometimes our sleeps just never wake the fuck up. God, that's so annoying. How can we debug this? Sometimes we have multi-core, like it's possible that some of the multi-core stuff that we added recently isn't helping. No. Where could we be getting stuck? I guess we'll just print here. We'll see. Print line before sleep 1. God, this is so annoying. After, we'll say before sleep 2. After, before sleep 3. After sleep 3. Why are we getting stuck? Oh, yeah, okay, so it's just getting stuck. Yeah, getting stuck during this sleep. So let's just double check. I think there's a chance that we've like really fucked something up here. So, well, I guess we know we fucked something up. So what is this guy doing? He creates a sleep future who says, hey, I'd like to request that we wake up at this time. And this is like the current time plus some sort of increase. So we'll say print line registering wake up for end. Hopefully that doesn't like fucking crash anything. Registering wake up for this. Good. Okay, so we do... Oh, sorry. Hold on. First of all, let's turn off this less thing. Oh, so that's not helpful. Before sleep 1. And we're just seeing like non-stop registrations. So he's registering a wake up. Somewhere we have like in our interrupt handler, we check if there's a wake up to happen. So let's see. Where is that guy? Wake up service. This isn't the guy. Somewhere we have like an interrupt handler that checks the time and tries to wake up. Interrupt handler. Probably this guy. Wake up if necessary. Yeah, this is what I'm looking for. So we look at times and we sort them by time. Oh, this is fucked. I see. So what I noticed here was that there were 2 wake-ups registered for the same time. Here, that we registered 2 wake-ups for tick 162. And the problem here is that we're only gonna execute one of those wakers, right? Because we are storing our like interrupt times as a mapping of use of this, like of timestamp to singular waker. And so this, unfortunately, oops, where did I go? We just have to make sure that we're storing all of them. So this guy needs to be a beachhead map of size 2 vec waker. And that's just going to break a bunch of shit. And we can just go through all the places where that breaks and see what happens. Yo, what's up? So here, can we use the mouse now? No, we've gotten to the point where we have discovered that the mouse exists, and now we are trying to set the address of the mouse in USB, so that we can like talk to it correctly. I think that there's like that's part of like the normal initialization. And then we got stuck with a bug in our sleep implementation that we're trying to fix up right now. So here we say let waker wakers, and for waker and wakers, waker wake by ref. Okay, so that works. Is there anything else that's not compiling? Lots of stuff. So 131, we are not using the right thing. So because the wake up service needs to turn this guy into a vec waker as well. Jesus. And then this guy needs to say, here when he's inserting the waker for this timestamp, he needs to first insert a default vector if it doesn't exist, otherwise append to that. So we say this interrupt times dot get or insert. Is there like an entry at time or insert vec new? Let vals equal this. I think so. This val should be a vec waker, and then we can say val.push waker. So I think that compiles. He wants me to say or default. Fine, I don't care. Cargo check. This compiles now, and if I cargo run, does that fix our fucking broken ass sleep? Fuck. I need to remove this annoying log. Let's check it. Okay, there we go. Yeah. Okay, sweet. So we're seeing after sleeps coming through, all happy like. So if we go back to our UCI thing, we were trying to reset the card again, so we can remove all of these before after sleeps. That's an annoying bug that has been fucking squashed. And now I think that we see two hello mix, but not the third one, I think, if I remember correctly. Let's see. Oh, we see three hello mix. So we see 1, 2, 3. And we'll just put hello mix 4 down here, just double check. So this tells us where we're going wrong. Yeah, okay. Okay, so here we're seeing that we successfully, according to our law, we think that we've successfully set the address of the device. But when we try to address the address the device with address 1 that we tried to set here, that's no longer working. Or I shouldn't say no longer working, it's just like it never finishes. And that makes sense, right? Because we like send this to the card and we say, hey, tell us when device 1 finishes talking to us, and it just never does. So we just get stuck forever. And so the question is, why is this address setup not applying? And let's see if he does anything crazy after he sets the address. No, right? All he does is he calls this set address function and then immediately just calls get descriptor again. So that's like similar to what we're doing. So maybe we should see if we're missing anything important from our address setup. So he's passed in this setup configuration thing, which is what we're doing with all zeros appended. We've put a 1 here because we think that we want to set address 1. He is setting the device address manually at that byte, which is what we're doing too. Right, he writes dev address here at byte 2 0 index, which is this one. So that should be the same as what we've done. He creates a queue of work that's done automatically for us. And then he sets the two things that he does is he does a setup token with data toggle, or what's the 8th bit here? In word 2, the 8th bit is device address. Right, so he's manually using device address 0 here when he's setting, which should match what we're doing. We are generating a thing with device address 0. The first argument here is address. He does say, oh, the second thing is token in. Is that what I did? I did token out. So maybe I need to do a read. Otherwise, the thing doesn't apply. Maybe that was my mistake. Oh, yeah, there we go. Okay, solid. So I think we have some form of proof that the address has been set, because we talk to address 0 here, and we then try to talk to address 1 here, and the second descriptor we read is still valid, which is a really good sign. So I think that we could argue that we're probably in a good spot now. And now, I think that I read somewhere Maybe USB HID for human interface device, I think is what's called. I think that now it's been set up. I think that that's all we have to do. And we might be able to just start calling this like function that tells us the position of the mouse. Give it a second. Give it maybe a few seconds. This OS dev wiki, I don't know what's going on with it, but he's slow today. For the past few days, actually. So I guess we can say that we are now working on getting mouse position. So he's saying there's just like a get report request that we could send out. We're supposed to validate that we have like a specific class ID, but I'm not really worried about that right now. I already know we have it, and I'm more interested in like figuring out what the process is. So he's saying the software can request a report from the USB device using the control endpoint and the regular setup packet. So I guess we need to figure out what endpoints it has, which I think might come from the device descriptor. Let's see. So get descriptor, and we can ask for interfaces and configurations. I see. And so the get descriptor response we can ask for the device descriptor, all USB configurations. All USB devices have at least one configuration. Does the device descriptor tell us how many configurations? It does. So it tells us here how many configurations we can have. And so here we can look at our response and see how many configurations this guy has. And here we see length, descriptor type. Why am I not seeing num configurations in here? I just only parsed up to the serial number? That's pretty funny. Let's check the configurations. Yeah, I just didn't write. Oops. Num configurations. This is bit 17, and we'll just tuck that guy in here. Okay. Oops. Oops, oops, oops. Okay. Oops. Oh, crap. I wanted to see the number of configurations. So I think I wait for this, I press Control C, and then I scroll to the right. Yeah, here we go. Num configurations 1. Okay. So we can kind of skip any configuration parsing for now. Then I think we can get configurations, and it'll tell us how many interfaces that he has. So let's try that. So here we can say for configuration in 0 to work 1 buff. And then we say that this is a USB device descriptor is what we want to parse this as. Num configurations. Okay. We need to pass this in as a slice. And then we say info getting configuration I, or we'll call this, well, yeah, we'll say I here. And this should be debug, actually. We'll remove these print lines. And now we generate a similar set of work here. Except here, I believe we changed this 1 to be a configuration. Because here we were sending a get descriptor request. And here we can say what type of response we're looking for. So here we're going to change this 1 to a 2. And the get configuration response is 8 bytes. right? So we'll allocate, we'll say, please respond to us with 8 bytes of data. And here we'll say we are 8 bytes long. And then I think we can do this work. And then we can probably print out got configuration response. And we can just print out work. I think it's the second thing that we sent, buff. And let's see what that looks like. So these are being sent to address 1. We're chilling. And let's see if we get anything back here. So we did get a configuration response for our single configuration. That's interesting. And here we want to know how many interfaces do we have. And so that's going to be byte 4. 0, 1, 2, 3, 4. So there's one interface. Now, I will eventually create a parser for this. But for now, we'll just say let interface num interfaces is equal to work 1 buff, the read response. And we're just going to say number 4. And then we'll say for interface in 0 to num interfaces. We want to get the endpoint. Okay. Yeah. So let's say that. We'll say, we'll do the same thing. But we're going to replace everything configuration with interface. We are going to replace the configuration flag here with the interface one. So this thing somewhere, where we're at get descriptor, we're going to replace the configuration thing with an interface thing. So we're going to replace that 2 with a 4. And then we're going to look and see how big the interface descriptor is. And he's also 8 bytes, so we're chilling. He's the same size as the configuration one, so we don't have to change any sizes. And we can just print out. What we get back. Let's see. Okay, so we got a configuration response, but then we have a problem after. That's interesting. USB get descriptor 1 unknown type 4 len 8. So that's probably, this is QEMU saying, what the fuck are you saying to me, man? Like, what the fuck is that? Which is interesting, because I thought, if I read this correctly, we should be able to call get descriptor with type 4. All USB devices must support requests for device configuration and string descriptors, but not necessarily interface. Oh, okay. So then how do I know about the interface? Am I high? Unknown type 4. It's saying that interface is 4. All right. Well, maybe we'll assume that we don't have to set the interface, but how do I know about like the endpoint? Each endpoint used for a particular interface has a descriptor which follows that particular interface's descriptor. When the host requests a specific configuration descriptor, the host cannot request a specific endpoint descriptor explicitly. An endpoint descriptor never describes endpoint 0. So in my configuration, does it tell me interesting? Somewhere, how do I get like the endpoint info? It is generally recommended the HID devices reports to the software using interrupt transfers, and that software should normally avoid the get report request mentioned above. Driver software should request a configuration descriptor for the HID device. HID must support at least one configuration. Then we should scan the endpoint descriptors, searching for the descriptor that indicates an interrupt in. So how do I scan the endpoint descriptors? That's what I'm trying to figure out. Because I don't know how many endpoints there are unless I can call get interface. let's see. So the device requests set address, get descriptor, set descriptor, get configuration, set configuration, get interface. Oh. Okay. So is get configuration and get descriptor with type configuration different? Maybe. Maybe. Note that the configuration descriptor index is not the same as configuration value in the configuration descriptor. Each configuration descriptor has at least one interface descriptor. Each interface descriptor can have up to 15 endpoint descriptors. When a host requests a certain configuration descriptor, okay, how do I get? What is there a difference between configuration and configuration descriptor? The device sends a 1 byte data packet during data phase, the control event transfer. The byte is the value of the current configuration of the device. A value of 0 indicates that the device has not yet been configured. It is in the address state. Behavior of the device is undefined if this request is issued while the device is in the default state. Oh, okay, so I have to set the configuration to get out of address state, I guess. So maybe I have to call set configuration. If the device is in the default state or the high order byte is not 0, W index is not 0, W length is not 0, then the behavior after the issuing this request is undefined. Okay. So where do I read about that? Address state. Okay. The host assigns the device a unique address, thereby transitioning the device to the address state. Then we request the device descriptor from the device via the default control point in order to determine the maximum data payloads as the default control pipe for the device. The host reads all possible device configuration information. The host selects a certain configuration from the list of configurations supported by the device and sets the device to use that configuration. Aha! Okay. So maybe I'll just call set configuration, which is this guy. And I guess we just pick one. So probably down here, we just set configuration. So I'll delete this interface shit. And here I'll just do this like setup read shit. And here my setup packet will have set configuration as its thing. So this is setup packet first byte is 0, second byte is 9, third byte is a little endian configuration value. So I think I just write 0 here because we have a single configuration. And then I set the index and length to 0. All right, and so now I do what I did over here, and I make my ACK just like a read, like this. And then do the work. And then I'll say finished to confirm that something actually happened. Let's see it, baby. Okay, so that did happen. And now can I call get interface? Let's try that. So get interface does this. The host uses this request to determine which alternate setting is used for a particular interface in the current configuration. Oh, so this will tell me which interface is being used, but I want to see like the interface's descriptors. So maybe I copy paste this guy and try him again now that we're like not in the address state. Maybe QEMU will bitch at me again, maybe he won't. Let's see. So we'll say getting interface 0. He doesn't like that I said append word instead of work. Let's take a quick little peek skis. So he still doesn't like QEMU still didn't like that get descriptor thing. I don't know if you saw that. Let's try it again. He says that USB desk get descriptor 1 unknown type 4 len 8. So I wonder if we like open up the QEMU source code, if that'll give us any clues. We can like see where it prints that. And yeah, he does just not support interface, hey? So how do I know? How do I know what the interface supports and what doesn't support? Interface. Request for configuration descriptor also returns all interface descriptors for specified configuration descriptor index. Oh, okay. That's interesting. A request for configuration descriptor also returns interface descriptors. So let's see that. He has this guy. Ah. Okay. So handle grouped interfaces if necessary. Yeah, okay. So that's interesting. So probably in this get configuration or get the configuration descriptors, we probably call it once, see the length, and then call it again with that much actually allocated. Let's see. So he does only say 9 here. 0, 1, 2, 3, 4, 5, 6, 7. So 9 is bigger than 8. But I am realizing that these 8 bytes we allocated are actually not big enough because this is index 8, which means size 9. So that's interesting. It's not like we're seeing we're not seeing this like length field increase. But it does also seem like he's not telling us these long, like the right size. Maybe we see extra shit after for the interface descriptors based off num interfaces, and we just have to allocate a big ass buffer. That would be interesting. So maybe we can try that. We can give it a big ass buffer when we request the configuration. Right, instead of giving it like 8 bytes, we can give it like I don't know, hex 20. Fuck it, blaze it. And let's just see what it says. Right, if we see it if we see it continue populating after, aha, see, it just keeps going. So that's interesting. So you have 0, 1, 2, 3, 4, 5, 6, 7, 8. Then these are the device descriptors here, right? 9, 4, 1. I bet you that's an interface descriptor here. So which of these guys tells me the number of interfaces? Offset 4. So 0, 1, 2, 3, 4, 1. And so this thing here is going to be my interface descriptor. He's going to say, I'm 9 bytes here, baby. Right? Then my descriptor type, let's see that, 4. So how do I see interface descriptor types? Let's see if that makes sense. Interface descriptor type. Should scan the endpoint descriptors, searching for a descriptor that indicates an interrupt in type. So how does this work again? If I look at the QEMU source code, when we request a descriptor, he appends the interface descriptor to it. And does the interface descriptor also append some shit? Yeah. He appends all the endpoint descriptors. Interesting. So we kind of have to just like allocate a big ass buffer and just know like to iterate the endpoints. That seems crazy. Like, how are we supposed to pre-allocate the right amount of size? Or like the right size? That's crazy. Can we look at this like get configuration descriptor thing again? Where did we see this? Probably here. Each configuration descriptor has at least one interface description. The host may request a specific configuration descriptor by its descriptor index, which is 0 based and has b-num configurations as returned by the device descriptor. Cool. Each configuration descriptor has at least one interface descriptor, and each interface descriptor may have up to 15 endpoint descriptors. Holy. When the host requests a certain configuration descriptor, the device returns the configuration descriptor, followed immediately by the first interface descriptor, followed immediately by all endpoint descriptors for that interface. This is followed immediately by the next interface descriptor. So how do I know how big that is? When a device has vendor or class specific descriptors that conform to the standard USB descriptor format, those descriptors are also returned interleaved among the... Jesus Christ. Therefore, the system software cannot assume continuous standard descriptors as implied by the previous paragraph. Instead, the system software should check the descriptor type and skip that descriptor if it is not a standard descriptor. Oh, okay. Note that the descriptor index of blah, blah, blah. So, I guess I make a big-ass buffer, keep like moving up by length, and once I pass... Like, for each length chunk, I check this descriptor type field, which is probably the second field in every single one of these, yeah. And from there, I can, like, collect my endpoint descriptions, and I can, like, keep track of those for given interfaces, etc., etc. And I think what we're going to do is we're going to just for now, to get a feel for what the fuck is going on, right, because this seems complex, let's just allocate like a big ass buffer. Let's try hex 80 for the size of our configuration response. And then maybe we can just find any endpoint for any interface by hand and use that to call this get report request. Or maybe we can just call get request. For now, right? The setup packet should be sent to the device endpoint 0. Yeah, okay. So maybe we can just try calling get report first. Let's make like a little loop where we just constantly call get report and see if when we wiggle the mouse around it changes. Now, obviously it's saying here, he's like, don't fucking do that, right? He's like, a real driver would find the interrupt endpoint. But I just want to like see any form of success to prove to myself that we're doing something sane. Okay, so what's this guy doing? Okay, first of all, this guy's also acting to the wrong address. Fuck, this is so my brain, it's like there's too much stuff in it right now and I'm getting lost. And I didn't write any comments here, so it's also hard to sort through anything. Okay, so let's get to my configurations. So let's just say that here we were setting the configuration, I think. Let's double check. So this is a 0009. So what was that doing again? Set configuration 0009. Yeah. So it's here is where we should be good to do shit. And I guess let's just call get report. So there's actually no get report thing in here. But maybe here, the software can request a report from a USB device using the control endpoint and the regular setup packet. The setup packet type would contain 0xA1. The request code for get report is 1. So what the fuck is 0xA1? Oh, here. That's the request type is 0xA1 is the first value. So I guess we say get report. So this is 0xA1. Then the request code is 1, they're saying. The setup packet's value would contain 0x0100 to request an input packet with ID 0, which is little Indian, so we'll try 0001. And the length field should be the length of the data stage the host wishes to receive. Oh, did I get this wrong? A101. So what is the value? So did he say that the value is 0x0100? Cool. Then we need to do index, which we can leave as 0, and the length, and we'll just say 8 bytes for now, just because we have no idea what the fuck we're doing, right? Like, we're just kind of guessing and checking at this point. Then we're going to need to read in that amount of data, probably. And then ACK it. Our read is going to be of 8 bytes. And then we're going to queue up that work. We're going to say that our ACK is data toggle, because we did before. And then we're going to do that work. And now, we'll make sure that all of these guys have address 1. We actually didn't make the setup descriptor, so we'll just quickly shove that guy in here. And let's see. Now we'll say print line, or in debug, I guess, got mouse position, mouse report. And this will be the second byte we sent. God, I hope to God that's right. Because we are really struggling here. Got mouse report, all zeros. Okay, so that's kind of indicating that we've fucked something up already. Let's just shove 1s in our initial read packet just to see if like the card has written anything here. Oh, okay, so that's interesting. So if we put all 1s, it's actually writing 1, 2, 3, 4, 5, 6 zeros, which kind of indicates that it's doing something. I wonder if we can like do this in a loop and wiggle the mouse around and see if anything happens. Oh! Okay. Okay. That did something. Let's try sleeping for like 100 milliseconds between requests. Which I think we do this. And let's just see what comes out of that. Okay, so I'll leave my mouse in the same spot. Oh! Wait, that's sick. Okay, so I'm definitely moving the mouse, and I'm definitely seeing it move. Now, we're getting locked up, right? But fuck that. We're definitely seeing something happen. Oh, and maybe we're not locking up. Maybe less is just... Hold on. Okay, keeping the mouse still, move it to the right. Hold on, let me... Oh, okay, yeah, it was just my thing was getting stuck. Okay, so I'm gonna hold the mouse still, move it right, move it down, move it left, move it up. Hold on. Wait, that's sick. Okay. So we've proven now that we are definitely... I'm, like, nearly certain that we're... Like, that's really good proof that we're talking... We're, like, getting the mouse position. Okay, so if I move it to the very top left, what do I see? 5168. So that must be, we must be seeing two 16-bit values that is the position of the mouse, right? If I move it to the very bottom right, I'm seeing like, oh, maybe not. Maybe it's a, hold on, we're gonna go top left again. so maybe we're seeing bottom left. Maybe we're seeing 1 byte followed by 2 16-bit values. So if I go top right, we see maybe like this. Hold on, maybe like this is the Y value and this is the X value, and they're little Indian, right? Because top right, I see a big ass X and a small, like relatively small Y. If I go to the bottom right, I see big ass both, maybe. I don't know. There's some format here, but at the very least, we're seeing movement. Which is pretty sick. Pretty sick. Okay. There's definitely more work to be done here. Specifically, this is not the mechanism that the OSDev wiki is suggesting we use. What we're supposed to do is we're supposed to iterate over all our endpoints and figure out which one is like an interrupt endpoint and use that. But I think that we'll leave that for another day. So I'm really happy with this. We've like proven, we've definitely like found the mouse. We've set it up. We've given it an address. We've put it in to like, we've taken it out of address mode and put it into whatever the next mode is called. And we're like spamming it with calls that give us something, right? We don't know what it is, but we know that this is surely saying something about the mouse position. And that's fucking sick. That is fucking sick. I'll come back maybe tomorrow, maybe the next day. I don't know if I'm going to take a break tomorrow. But pretty happy with that. So, if you liked what you saw, I stream most days around 1 or 2 o'clock Pacific time for around 1 or 2 hours. If you miss live, there's a YouTube channel linked in the Twitch description that has all the VODs uploaded to it. And if you're watching on YouTube and you want to come say hi, give suggestions, whatever, chat, there's a Twitch link in the YouTube description. Probably next up is I'm probably going to try to parse those interface endpoints correctly. So this like monster of data, this guy, this is like a get configuration response. He's going to give me some interfaces, some endpoints, and I'm supposed to find the correct endpoint to give me an interrupt descriptor. But yeah, I think that like we've also kind of proven today that like the interfaces that we've set up for like queuing up USB requests, they're definitely like workable. There's like some like cleanup that we could do to make it a little easier to work with, but like it's now easy to just like chuck work at the wall and wait for it to come back, which is pretty sick. So we'll be using that in the next few streams to try to figure out how to like write like a proper mouse driver. And then there's like, right now we've kind of got everything in this like one file in this one spot. Almost certainly we're going to have to like block that out into like a proper driver hierarchy where you have like the USB layer, the host controller layer, and the like mouse driver layer. Yeah, so that's what's coming up next. If you liked what you saw, feel free to come back. Thanks for watching. Catch you on the next one. Bye.